about our journey to understand mechanical fatigue failures for our 3D printed PLA shafts. We're hoping to apply our classroom knowledge to our real-world experiences within our xLab, with the mission of predicting the number of cycles until failure for the shafts in this experiment.
Our initial trials involved hanging weights from strings attached to the bearings, but we soon realized a flaw with this specific setup. This introduced forces in both the X and Y directions, affecting our 4-point loading model.
This can be better illustrated in this free body diagram. Our mass hangs here in the center of the shaft and imparts a downward force. This force also acts on the bearings, but since the mass is at an angle, there is a horizontal force that imparts a torque on the shaft and creates a bending moment, which introduces forces we have not accounted for.
To eliminate this unintentional torque, we introduced a strain gauge load cell. This allowed us to refine our setup, achieving the precise 4-point loading we were aiming for. This also enabled us to determine reactions and draw the shear and moment diagrams for our model.
To determine the reaction forces, we use this model here, and then the sum of the moments and the sum of the forces to determine that reaction force A equals reaction force B equals F. So this force equals F, and this force also equals F because our 4-point bending moment. And from that, we're able to determine a shear and moment diagrams. We know that we have a force applied on the beam that has a magnitude of F at this point, so we go up F, and then once we get here, we have a force down of F that brings us back to 0, and we're at 0 all the way until we get to this other F, which brings us down here, and then we reach this F, which brings us back up to here. This makes it very easy when we get to our moment diagrams, because we know that this is a distance of A between the reaction forces and the downward applied forces. So we know that this magnitude is going to be F times the distance A, and that magnitude stays the same all the way until we get to here, and then descends the same amount back down to 0 with these two forces.
Using these shear and moment diagrams, we're able to find the critical location of bending on the beam. Since the moment's constant throughout the length of the beam, we know that the critical location will be here and the center where the diameter is smallest. Now, using the formula for bending stress, which we know is mc over I, and then we can break this down into all the pieces. We know that m is equal to force times A, which is the distance from this load to this load. And then C is the diameter over 2. And the moment of inertia for a circular beam is pi over 64 times the diameter to the 4th. Now, simplifying this down and canceling out like terms, we can reduce it to 32 F times A over pi times the diameter cubed.
The next step in this process was that we needed to understand the endurance limit of our material. This was actually a very complicated exercise because none of the shafts we were testing were 100% infill, so it was very difficult for us to use that equation that we had using the ultimate strength. So in order to take that into consideration, we would multiply by a scalar factor alpha onto our calculations for the endurance limit, and then we also had a surface modification factor that we calculated as 0.5, the size modification factor that we calculated as 1.07, and then the load Kc was equal to 1 because we were using bending loading.
To move forward with our calculations and finding the number of cycles to failure, we needed to find F, the fatigue strength fraction. Now in class, in exercises, we use this graph. However, our material, PLA, the tensile strength is not on this axis from 70 to 200, so we needed to extrapolate this graph and test for different values in order to see what would be the most successful.
Once we have the fatigue strength fraction, we have all the pieces we need in order to calculate the number of cycles until failure. We're able to calculate the constant A from this equation right here, B from this equation right here, and then put it all together, knowing that we calculated sigma rev earlier in the experiment in terms of our load F. We were able to get our final value for expected number of cycles until failure.
Throughout this process, we realized that it's very important to look at noise and interference when dealing with a data set. Noise is any random variation within the data set, and interference is any unexpected trends that can be seen in the data. Once we had pulled data from our first few trials, we saw that there was no interference present, but a fair bit of noise. This can be attributed to the assembly shaking and rattling while the motor was running. It could just be due to an imperfect fit of the assembly or any other external factors. Now, to account for this noise, we needed some baselines. So we calculated the average, 2-minute average, and 5-minute average load cell data reading and compared that to the total number of cycles. To account for extrema, we looked at the maximum and minimum values, and then to exclude any outliers from our data, we took the average plus or minus 1 standard deviation.
Once we got those values, we decided to plug them into our projection that we calculated earlier in this exercise, and we found out that these numbers didn't work. It was very clear right away, all the force values that we were entering in were yielding number of cycles until failure that were near 0. So, to better understand the situation, we actually went ahead and graphed the number of cycles until failure versus fatigue factor F and miscellaneous modification factor KF, which were two of our biggest assumptions and areas of question throughout this exercise. So by plotting a range between 0 and 1 for both of them, we were able to understand all possible playouts of this exercise. So you can see from this that it's very clear that almost every combination of KF and F, we get a number of cycles predicted that is basically 0, except for right here where we see an asymptotal value that approaches 10 to the 292nd, which led us to believe something went wrong.
After looking at this graph, we realized that the equations we were pulling from Shigley's that were all used for steel could not be applied to our experiment for any value of the force. The material properties between steel and PLA are far too different, and there was just no conclusive data that we were able to pull using these equations, so we took to the other.
Once we realized that these equations were not applicable to our experiment, we decided that we were going to go through, collect enough data points to reverse engineer an SN curve that allowed us to correctly predict the number of cycles till failure. Sadly, we did not have enough time to do that throughout the course of this xLab exercise, but we were able to find a paper online that predicted fatigue on 3D PLA from the University of Sheffield. On this website, we were able to see from their experiments, they were able to calculate an SN curve that we were able to actually use to predict numbers of failures that were much more accurate than those that we got from the steel calculations.
Although we came up a bit short with our experimental data, our whole team is very passionate about the supplemental work and hope that our exercise can be carried forward by future xLab groups.